Welcome everyone. Today we have a guest lecture on atmospheric lidars by Robin Wing, who's a postdoctoral research scientist at Institute of Atmospheric Physics, the Leibniz Institute of Atmospheric Physics. He's an expert on pretty much anything related with lidar and lidar techniques, and he's definitely a good person to give you an overview talk about the topic of lidars, and which I personally don't know much about. So I'm looking forward to learning a lot today. A little bit of background about Robin. He's from Canada, so he did his undergraduate and master's at the University of Western Ontario. He worked for a while as a research scientist at the Geophysical Institute in Alaska, University of Alaska Fairbanks, and he did a PhD in France at an institute that I cannot pronounce. And then he also did a postdoc there. Maybe you can say the institute name. I mean, it had Laplace in it, which sounded pretty fancy.
Yeah, it was the Latmos Institute in Paris, specializing in atmospheres, oceans, and other planetary atmosphere.
Yeah, so carry away.
Okay, so sounds good. So thanks for the introduction. Today we'll talk a little bit about atmospheric LIDAR. I wanted to start off with this nice photo. This is the wind LIDAR that we constructed in Kühlensborn in northern Germany. So we have one beam that goes to the north, one vertically, and one to the east. And with this, we're able to measure temperature and wind from about 30 kilometers up to 90 kilometers. Which is really a rather exceptional feat. There are currently only 6 other instruments in the world capable of measuring temperature and wind in this altitude range. So it really is an unexplored part of the atmosphere. Okay, so just a little outline of how I'd like to go about this talk. I'd like to roughly keep this timeline. I'll try my best. So I'd like to start off with a little bit of a review of the atmosphere and spectroscopy. And then we can't talk about LIDAR without understanding a little bit about atmospheric scattering physics. So how light interacts with gases. Then I'll briefly touch on how a LIDAR works, the basics, the hardware, and some of the basic math. And then a little bit of a break. And the end will be fairly easy. It'll just be a picture show of what's possible with LIDAR in the atmosphere. Okay, so let's give it a go. A brief review of the atmosphere. So the standard structure of the atmosphere looks something like this. Near the bottom, we have the troposphere, where most of our weather is. In the middle is the stratosphere, and the important point here is the ozone layer, which protects us from ultraviolet radiation. Above, we have the mesosphere, which is a really interesting layer that's dominated by gravity wave dynamics, tides, and very large planetary scale processes. So it's a really exciting region, but also quite difficult to measure. Above that, say above 100 kilometers, we have the thermosphere. And then a little bit higher is the exosphere. And we can also consider that there is ionization in the atmosphere as well. So here's an electron density profile, and you can separate the atmosphere into different regions, which correspond to different letter designations. So the D region, E region, F region, and so on. And below, we see sort of a schematic of how you measure different parts of the atmosphere. So here we have LIDAR. It's going up with multiple beams to roughly 100 kilometers. You can use radar to do about the same. So you can measure winds from meteor trails. You can measure it in the troposphere, etc. You can use cameras and other optical techniques to measure air glow and aurora up near the top of the mesosphere. You can use sounding rockets above, say, 60 kilometers up to close to 130. Or you can use satellite instruments, a very high, low Earth orbit, just above 300 kilometers. Also balloons. Tropospheric balloons are most common, up to 30, but you can have some long duration stratospheric balloons. But I'd unfortunately like to inform you that this slide is already outdated. This is a more accurate view of what's possible with LIDAR. So LIDAR is a very flexible and powerful technique, which allows you to measure the atmosphere from the surface up to about 750 kilometers, depending on what you'd like to measure. So that was the structure. Let's talk a little bit about the composition. This is a fairly standard slide out of a textbook. The atmosphere is mostly nitrogen and about 20% oxygen and 1% trace gases. Here is a list of the relative percentage by volume of each of these different gases, trace gases, plus nitrogen and oxygen. And there are dedicated LIDARs for measuring each of these species, except for argon, neon, and krypton. Does anyone want to take a guess why these three gases are difficult to measure? That's okay. I'll ask the question again in about 5 minutes. So how do we measure these different gases in the atmosphere, especially if their percentage by volume is so small? Like look at methane, 0.00015% by volume. Well, the way we do that is we use spectra. So for every atom in the atmosphere, it has a corresponding atmospheric spectrum. So if you know a particular wavelength, let's take, say, for example, NH3 here, you could lock your laser and detector system onto a very strong line, and that would serve as a spectral fingerprint for that atom. No other atom in the atmosphere would emit light at that wavelength. So some of the most common measurements made by LIDAR for atmospheric composition are ozone, water vapor, methane, and carbon dioxide. But any other species that you can find a strong line for and buy a laser source that emits on that line, you can make a LIDAR measurement with. So what happens to create these sets of lines? So every atom or molecule has a unique set of energy transitions. That is to say that when a photon interacts with the atom, it has a probability of being absorbed, boosting an electron up to a different energy level. And then when that electron relaxes, the atom has to emit a photon to get rid of the energy. And that photon corresponds to a quantum energy transition, and each of those transitions has a probability. So combining this information together, we know that the color or the wavelength of the light and its intensity, we can measure exactly what we can know exactly what we're measuring from the color and how much is present from the intensity. So here is I just wanted to show this. This is something that one of my colleagues made very recently, the last few weeks. This is to give you an idea of what kind of lines are available. So this is a map of moderately strong lines only from the ground state for the first 89 elements on the periodic table. And I just want to show you that there are a huge number of lines that are accessible, and it will probably take us decades to map out all of them with a LIDAR. And this is a very simple set of atomic lines, but there's really an endless sea of possibilities. Currently, I'm working mostly with this line down here, 680, and in the future, I'll add in a 589 line too. So this would be for lithium and for sodium. So a brief review of what we've covered so far. The atmosphere is divided by temperature gradient into the troposphere, stratosphere, mesosphere, thermosphere, etc. We can distinguish between multiple atomic, molecular, and ionized species based on their wavelengths. And each of these wavelengths is a spectrally unique signature corresponding to a single target species. So this is how we're able to measure a single target species in the atmosphere with LIDAR. Okay, so that was the atmosphere. Now let's go on to scattering. So how light interacts with atoms and molecules. So when a photon goes up and it encounters an atom or molecule, it has some probability of scattering. And scattering is just defined as an interaction with an atom, so an absorption and a re-emission in a different direction. So here's this little cartoon here. A photon comes in, it boosts an electron from this orbital into this orbital, and then sometime later it has to relax again. So that's the absorption side. And sometime later it has to fall back down to the original orbital, and it emits a photon. So I'll ask the question again. Can anyone tell me why it's difficult to measure argon, krypton, and neon with LIDAR? That's okay. The answer is because these are noble gases, and the valence shell of a noble gas is full. So it takes a great deal of energy to bump an electron out of that nice stable shell. So these noble gases are quite difficult to measure. Okay, so the very simplest form of scattering is elastic scattering, called Rayleigh-Cabane scattering. This means a photon comes in. So I often describe photons as HV, so Planck constant, and V is the frequency. So just a brief clarification, I sometimes refer to frequency, wavelength, and color as the same thing. If you get confused, please, it's just my sloppy terminology. So the idea is a photon comes in, it boosts an electron from a ground level up to what's called a virtual level inside an electron shell. So this this virtual level has an energy. And when the electron wants to relax again back to the ground state, it emits a photon of the exact same color or wavelength. So HV in, HV out. So if I send in green light here, I get green light out here. This is also the answer. This Rayleigh-Cabane scattering is the answer to the question why the sky is blue. So if we want to describe scattering mathematically, this is the equation we would use for the Rayleigh-Cabane's approximation. We would say that the scattering intensity is related to the initial intensity of the light, and then some mathematical terms which involve wavelength, particle size, index of refraction, etc. But to keep it simple, we'll ignore most of the equation, and we'll say that scattering is proportional to the initial initial intensity times lambda to the fourth, so minus 4. So the scattering intensity goes as the inverse fourth power of the wavelength. So if we take a look at our little color blow up here of the visible spectrum, 700 nanometers is a much longer wavelength than 400 nanometers. So since it's an inverse power law, blue light will scatter much, much more than red light. So we have much more Rayleigh scattering of blue light in the atmosphere compared to red. Okay, so unfortunately, there's more than the simple elastic scattering in the atmosphere, or fortunately or unfortunately, however you choose to see it. So pure elastic scattering would be this central peak here, this Rayleigh-Cabane's line. This would be green light in, green light out. H nu is equal to H nu, pure elastic scatter. Then we have these little side lobe lines. These are called Brion lines, and they are a result of phonon-photon interactions inside a scattering target. For most of the atmosphere, these lines are very, very small, particularly as you get higher and higher into the atmosphere, because the density is so much lower. The probability of having phonon-photon interactions essentially disappears. But these Brion lines should be remembered if you're ever measuring something near the boundary layer, so down near the surface, where the atmospheric density is high. If we consider this entire central component, sorry.
Robin,
yeah.
is it okay if I interrupt or?
Yep.
So what would be phonons in the atmosphere? Would they be sort of?
They would be photon-photon interactions within a scattering material, so potentially an aerosol or a molecule.
Okay, so it's within a sort of a. It's not. This is not atmospheric
No, no.
Okay.
Yeah, sorry.
This is within
Okay.
like an aerosol. Okay.
Yeah, these is, I just touch on it for completeness. It's really a property of the very low atmosphere. I'll talk a little bit more about how you can use it to get temperature later on. Okay, but if we consider the entire central component of the scattering intensity function, we could call this entire red box as Rayleigh scattering, but it's a little contentious. I know if you want to be cool on a Friday night, you could go out and try and impress your date by calling everything in the central band Rayleigh scattering, but you could start a bar fight depending on how the company is mixed. Okay, within this central Rayleigh-Cabanes line, there is quite a lot of structure. So if we see in this little inset that I put in here, we see that there is the central Mi-Cabanes peak in the center, and then there are these side lobes. These side lobes are very temperature dependent, and these are called rotational Raman lines. And they're quite useful if you want to get temperature out of an otherwise very difficult part of the atmosphere to measure. I'll talk a little bit more about that later. But the key point here is that this nice smooth distribution that I'm showing is not realistic. It looks something more like this, a bit of a mess with many, 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 many lines. Okay, so we've talked about elastic scattering. So that is no loss of energy. So green light in, green light out. But we also have inelastic scattering, where the photon either exchanges energy with its target atom. So it either gives energy and comes back at a longer wavelength, or it gets energy from the interaction and comes back at a shorter wavelength. So the example we have here is we have the blue line up and the red line down. So this is elastic Rayleigh scattering. Stokes, so the loss of energy, we have energy coming, incoming energy photon, and then we're emitting less energy. So some energy is remaining with the atom. So the emitted photon is at a longer wavelength. And then we have anti-Stokes Raman scattering. So we get energy emitted and absorbed by the photon, and then emitted more energy. So energy is taken from the target. So green light in, blue light out. So these energy modes, these inelastic Raman modes, correspond to rotations within molecules. So they're also called rotational Raman lines. So for example, if we have water vapor here, you can have these degenerate Raman energy levels based on rotation around each of the different axes, as well as rotation like this. So there's different places that energy can be quantized. And this entire set of lines, as we see here, is temperature dependent, which will allow us to use it later on in the lecture. Okay, now there is a second set of Raman lines called vibrational Raman lines, and these are out here in the wings, these side lobes out here. Whereas before we saw that there was rotation around symmetric or asymmetric axes within the molecule, we can also have vibrational energy levels associated with bending of a molecule. So if water vapor is flexing back and forth like this, that can have quantized energy states. And we can measure the light that is emitted from those states. If we were to sketch it out as an energy diagram, we would see here that if we wanted to go from a ground state energy line here up to the next the next electronic energy level, that's a very large distance. So it requires a lot of energy. If we want to go between vibrational levels, so say we want to go from level 1 here to level 2 here, these correspond to vibrational energy modes, they're much, much less. And the rotational energy levels that I'm showing here are even smaller. So if we want to rank them in order, electronic transitions require a lot of energy, so they have a higher probability. Vibrational energy levels have a much smaller energy, and the smallest are the rotational Ramans. And all of these energy levels are discrete and quantized, meaning that you know exactly what you're measuring at any given frequency. The next type of scattering I'll talk about is called resonance fluorescence scattering. So this is like elastic scattering, but what you're doing is you're hitting the atom at a resonant frequency. So if you illuminate certain atoms with a particular wavelength of light, they can amplify the emission of that light quite strongly. They really backscatter that light very efficiently. And you can see this on Earth when you look at street lamps, particularly the ones that look kind of yellowy, like this color that I'm showing here. This is this yellow color in old street lamps is located to the sodium D2 doublet line. So it's a very famous sort of emission line, and we can do lots of fun stuff with this in the LIDAR. The D2 name just comes from an old naming convention from the 1800s, where they were looking at solar absorption spectrum. So this is a solar spectrum. And all these different elemental absorption lines are either coming from gases in the solar corona or in the Earth's atmosphere. And this little dip here too, it corresponds to the absorption in Earth's atmosphere of the from sodium at 588 and 589 nanometers. So here we can see what that looks like and how we could potentially use that to measure temperature. So if there are two lines, and these two lines are formed by the Zeeman effect. So this is spin-orbit coupling. So in a weak magnetic field, you end up splitting these lines. So if there's one line here with no weak magnetic field, the Zeeman effect preferentially pushes some electrons into a different spin orbit. And then you get slightly weaker and slightly stronger lines. And this is called a hyperfine structure. But that's not really important for now. The important thing is that it's useful. So when we measure this in the atmosphere, we don't measure nice, clean, perfectly, infinitely narrow spectral lines. Because we're measuring a gas, there's always a thermal broadening of the line. So if we take a look at this 500 Kelvin line, we see that we don't even measure two lines. We measure this kind of double humped feature. And based on the broadness and the shape, we're able to determine what the temperature is of the sodium atoms at this particular time. If we measure it at a much colder temperature, I'll speed up, we see that the lines become much more distinct as the gas cools and the number of and the thermal motion decreases. Okay, almost done this part. Okay, so what we've talked about so far is elastic scattering, inelastic scattering, resonance scattering. The next thing is me-scattering. So all the previous scattering was off of atoms and small molecules, where the particle size is on the same order as the wavelength of the light. So the 50 nanometer particle size is on the order of 530 nanometers for green light. But now we're talking about scattering off of large particles, so water droplets, ice crystals, big aerosols, or clouds. And in this case, the particle size is much larger than the scattering frequency of the light. So you can imagine sunlight coming in. And when it comes through the blue light, it scatters sort of isotropically due to Rayleigh scattering. However, when sunlight comes into a cloud, it scatters much differently. Quite a lot of it is reflected backwards, and some of it is multiply scattered downwards like this, and you get a more diffuse looking light source than you do from a clear blue sky. Okay, so that's all the different types of scattering that I want to talk to. It's just a few more interesting and useful concepts to discuss for scattering. Light is also polarized. And one of the big properties of laser light is that it's linearly polarized. So when we fire a laser, we're not firing alternating electric and magnetic fields like this or in a random orientation. all of our electric fields are in one axis. So this is called linearly polarized light. And we can make use of that because different shaped particles in the atmosphere can change the polarization when they scatter light. If we have a spherical particle like a cloud water droplet, then there is next to no depolarization. So the polarization you send up is close to the polarization you get back. But if I have an ice crystal that allows multiple internal reflections, or something that's crunchy or abnormally shaped like an aerosol or soot particle, then we can get depolarization. So if I send linearly polarized light up, I get some light coming back in the opposite or perpendicular polarization. And then I can do a ratio of the polarization up and the polarization back to find out what I am measuring. So am I measuring round particles like water vapor, or am I measuring crystalline particles like ice? Here is an example where you can use depolarization to say that the signal coming in this yellow box is from water, and what's coming from this cloud is ice. So the cloud we're measuring in this picture is ice because it has a high depolarization ratio. Okay, last little thing, Doppler shift. So in addition to having polarization, we also have Doppler shift. So this is the effect, Doppler is the effect of shifting the frequency based on the relative motion of the advected air parcels. So if air is blowing away from your laser, it will blue shift the light. If it's blowing, if it's blowing away from the laser, it will red shift your light. If it's blowing towards you, it blue shifts it. This is a very similar concept to in astrophysics. And we're able to measure this shift in central frequency and determine wind speed using the Doppler shift. So a quick summary of the scattering that we've covered so far. We have elastic scattering, which is mostly Rayleigh-Cabanes. It has the properties of polarization and resonance. We've covered knee scattering, and we've covered Cabane scattering. And we also have inelastic scattering, the rotational Raman and the vibrational Raman. Here is a little schematic. I won't go through it, but it's useful for you if you ever want to remember how these things relate to each other. Okay, and a quick summary of some terms you can read later, but things that we've talked about or I've mentioned: absorption, resonance fluorescence, scattering is the big one, which is a change in direction of the photon by absorption and re-emission. Extinction, backscattering means scattering by 180 degrees. Elastic scattering, knee scattering, Rayleigh scattering, Cabane scattering. Rotational Raman, vibrational Raman, Brillouin scattering, resonant absorption, and depolarization. Okay, so that's the first little bit summary of the atmosphere and of scattering processes in the atmosphere. Any questions so far?
Any questions? Well, I have a question. So
Yes.
are there any time constants involved in these different scatter?
Yes. The time constants are determined experimentally, and they're used in determining how effective the scattering process is. So you're able to use a time constant to calculate what's called a backscatter cross-section. So if you imagine laser light going up, each atom has an effective backscatter cross-section, or how efficiently it will backscatter light towards you. And it changes based on the different types of scattering process. So resonance scattering has a very huge backscatter cross-section, whereas rotational Raman has an extremely small, maybe 6, 7, 8 orders of magnitude smaller than elastic scattering. And these are all based on the time constants for how long it takes for an electron to reach an excited state and relax and re-emit.
Yeah, because there's some auroral emissions that have quite long radiative lifetimes, and I'm wondering if you use any of those with LIDAR as well, or do they have such low cross sections that they're not worth it?
Yeah, that's a good point. So the auroral stuff, I guess if you're trying to do really high altitude stuff, you could think about it. But what we do is we put very narrow spectral filters in front of our LIDAR detectors. So anything that's outside, say, half a nanometer from our chosen line, we're blind to it. Does that make sense? We put very narrow filters in front of our detectors. Did that answer the question?
Sort of.
Okay.
I'm wondering, like, let's say, well, maybe just to, I'm a complete novice when it comes to LIDAR. But let's say you emit the LIDAR pulse, and if you create an excited state, and that excited state has a long lifetime. It takes, I don't know, 1 second on average for that excitation to release.
Yeah.
Would that be too long of a time between excited emission?
Yes, so that would show up in subsequent acquisitions. So we have this problem when we're doing resonance scattering. And what we do is we calculate our laser power, and we keep it, the laser power density, low enough that we avoid these saturation problems. Because what we want is that a laser pulse goes up, interacts with an atom, and comes back and is detected before we send the next pulse up. If we have a 1 second relaxation time and a 50 hertz acquisition system, we're smearing out our return signal over many pulses.
And you would no longer be able to measure range because your
Exactly.
flight is not measurable anymore. Oh,
Yeah,
Alex has a question.
We would definitely do the calculation and keep our energies low enough that this problem disappears, or choose a different wavelength.
Alex, did you have a question?
Yeah, about the LiDAR, like the measurements, they still require to do atmospheric correction, like an account?
Yes, yep, that's in the next section.
Okay.
Yeah, okay, so let's get to it, and we'll satisfy that curiosity. Okay, so LiDAR in itself is really a very simple process. We have a laser source at the bottom, and the laser sends out pulsed light. And as the light goes up in the atmosphere, it scatters off of a target, either an atom, a molecule, or something like a cloud droplet. And then that backscattered photon comes back down to the telescope, where it's collected and focused into a detector system. That's all there is to a LiDAR. So a few other interesting things, we find out the ranging. So Z is 2 times the speed of light times the travel time it takes. So if it takes some amount of time to get up to here and here, that's 1 altitude. But to get to the very top, that takes quite a bit longer. So based on the return time of the photon, we can calculate the altitude it came from. And what does a raw LiDAR signal look like? A raw LiDAR signal will be proportional to atmospheric density, and it will look something like this. So this is an exponential decrease in signal with altitude. So this is a log X scale, and we see a more or less straight line. And if we were to fit a scale height from this, we would find the atmospheric scale height. The uncertainty on this signal, since we're counting individual photons, and these photons have a Poisson distribution, the uncertainty will be 1 over the square root of the number of counts in each altitude bin. That will be the fundamental uncertainty on our measurement. It's also worth noting that we don't need to count individual photons. If I were to want to go to a lower part of the atmosphere, with a much higher signal, I could also use analog counters. So this would be illuminating a detector with light and immediately converting that into a voltage and measuring a voltage. This would have a different uncertainty than pure photon counting. It would have a voltage uncertainty as opposed to a photon uncertainty. But that's a little bit too much into the details. We can describe this equation that we saw on this plot that we saw on the previous slide with the following equation. It looks really complicated, but it's very simple. It's like the Drake equation. So the number of photons at each altitude, nz, so this guy here, is equal to some system efficiency correction, I don't know, 0.7. This varies between each LIDAR. It's the amount of light that you lose for reasons that you don't know why. And then to answer your question before, we need to correct for the transmission as a function of altitude of the laser light going up at every given wavelength. So say we're emitting at 532. We need to take an atmospheric model and calculate the transmission of the light going up at 532. And say we were doing elastic Rayleigh, then we're measuring at 532. So we also do the correction downwards at 532. But say we're doing a Raman measurement at 608 nanometers, so sending up 532 and receiving at 608, then the correction upwards is at 532 and the correction downwards is at 608. The next term is called the geometric overlap function. And this is, if you've ever, what I want you to do is hold your finger up in front of one eye and move it very slowly towards your eye. And the place where you start to lose focus is the overlap altitude. So the overlap range. That's the exact same as a LIDAR. It has a minimum altitude at which we no longer efficiently focus photons into our detector system. For my system in Kuhlenborn, it's about 12 kilometers. I don't see anything correctly below that altitude. The next is just a laser power term. So the more power you put in the laser, the more signal you generally get. The next term is this sigma cross. So this is the backscatter cross section. This is the experimental parameter that determines how efficiently a molecule like nitrogen would backscatter light at, say, 532 nanometers. The next term, this NZ, is the atmospheric density as a function of altitude. So the more air there is, the more probability of backscatter, the more signal we have. The next term is just the area of the telescope. So the larger the telescope, the more light you generally collect. However, we do have to make a correction by 4 pi z squared. And if you look at this, you'll see why. As we go up in the atmosphere, the angle that we subtend gets quite a lot larger. And the range goes as z squared. Because we're looking up through a spherical volume, some subtended area of spherical volume. The final few terms are pretty simple. Delta t is the integration time in time. So say we're running at 50 hertz, then we have an integration time 50 times per second, 1/50th of a second. Delta z is our vertical integration. So say we're measuring at 1.5 meter vertical resolution. That's our integration. The final term is the background term. This is a catch-all term for any sort of emission that doesn't come from our laser. So this could be both thermal emission inside our detectors, could be moonlight, sunlight, starlight, light from the lab, all other sources of background light. And it is generally a constant as a function of altitude. If it's not a constant as a function of altitude, we have a systematic problem and we have to fix it. Okay, that was enough math. So let's look at the components. The principal component of a LIDAR is the laser. So laser means light amplification by stimulated emission of radiation. And this is a very descriptive word for what it means to do a laser. It says exactly what it does. We amplify the light by stimulating emission. And what does that mean? So the first component of a laser is called the pump, the optical pump. And what we want to do is we want to put lots of pump light, or sort of white or broad spectrum light, into an optical cavity called an oscillator cavity. The oscillator cavity is what's going to select our frequency and start generating the laser light. There are a few different ways that people pump an optical system. The old school way, or most common way, is flash lamps. So basically high intensity light bulbs. And you just charge up a capacitor and you just flash these guys at, say, 100 hertz. And you pump a bunch of white light into your oscillating cavity. A more modern approach is to use diodes and say, okay, my laser pump source operates most efficiently between 200 and 300 nanometers. I don't know. So I will pump it with 250 to 280 nanometer diode pump. So you're not wasting all that extra white light and heating up your laser for no gain. You can also create a laser through pure electrical discharge. So you can have a huge gas cavity and just discharge electricity into it. Those lasers are pretty scary. Okay, but let's get back to the idea. The idea is that we want stimulated emission. And so when we optically pump our cavity, what we're doing is we're dumping energy into a lasing medium, usually a crystal, and we want to boost all the ground state atoms within our crystal into their excited state. This is called population inversion. Normally, there are more ground state atoms than excited state atoms. But to make a laser, we have to flip it. We have to have more excited atoms than ground state atoms. Once we get this population inversion, we start getting this sort of back and forth motion of the photons. So this is a sort of schematic of a laser oscillator. On one side, we have a 100% reflective mirror. On the other, we have a mirror that's slightly less than 100% reflective. And the lasing medium in the middle is usually a crystal, but it can be a dye or a gas or anything. So we pump the light, either with flash lamps or diodes, into the side of the lasing crystal. And when we set our cavity, we have it in such a way that the desired wavelength of light will oscillate backwards and forwards in the resonator cavity. Photons, which are not the correct wavelength, will preferentially over time be scattered out of the lasing cavity. And then once we have sufficient energy built up within the cavity, we want to have this come out as a laser pulse. So how do we do that? We use what's called so this is the Star Wars thing. We don't want a continuous wave. We want pew, pew, pew. So we use what's called a Pockels cell. So it looks like this inside the laser. And what it is it's a piece of optical material, so a crystal of some sort, but it has a unique property. It changes the refractive index if you apply an electrical current to it. And by changing the index of refraction, we can flip the polarization of the light. Remember at the beginning I said laser light is always linearly polarized. So if I want to open the laser and send out a blast of laser light, I put on a little bit of electrical current, and it switches the linear polarization from vertical to horizontal, and it comes out. If I want to turn it off, I shut off the electricity, and it's all in the vertical polarization still, and it just keeps going back and forth inside the oscillator cavity. So if I want to let it out, I put a quick little TTL pulse of voltage across my Pockels cell, and pew, some light comes out. And then I let the energy build up again within the cell, and then another pulse, laser light comes out. And you can do this very fast, kilohertz. It's very easy to do. Okay, so that's the laser. Next step is telescopes. So again, if you remember the schematic, we sent light out, it went up, scattered in the atmosphere, came back, and now we have to detect it in a very large telescope. This was my master's project a number of years ago. It's 2.65 meter telescope for measuring Rayleigh signal in the very high atmosphere. So it's generally the larger you can make your telescope, the more light you can collect from higher altitudes. However, the trade-off is large telescopes can be extremely difficult to focus to a very narrow point. This tripod is mounted like 3 meters or so above the ground. It can be a little difficult to focus all of your light efficiently into your detection system. So how do we detect single photons? Say I want to measure one photon that backscattered from 80 kilometers. That seems really difficult. What we use is something called a photomultiplier tube. It looks like this. They're very small. And what's happening inside is it allows us to convert a single photon into an electrical signal that we can measure with electronics. So an incoming single photon comes through a photocathode. So photocathode means positive voltage. There is a focusing voltage applied, and then it's put onto a photoelectrode. So the photoelectrode, the photon will hit this photoelectrode. It will cause one electron to come off and cascade down the dynode chain. And each time you hit the next dynode in the series, there's a drop in voltage, and you get one. So one photon causes one electron causes two electrons. Two electrons cause four electrons. Four electrons cause 8 electrons, and so on down the dynode chain until you reach the final anode, so the final negative voltage point. And there you can measure it. What is the actual voltage? So the more photons you have coming in, the more voltage you can have at the end. And this also allows you to convert a single incoming photon into a detectable voltage. And so this Robin, is what allows. Yep.
Can I make a question here? So just to clarify, so you have an incoming photon, and
yes.
Where does that photon get converted to an electron? Is it at the photocathode or?
Yes. Yep. So it hits here and it pops out an electron.
So you use the photoelectric effect, and then.
Yes. Yep.
Now you have the electron that then.
Yes. Sorry, I think I misspoke then. One photon kicks out an electron. Yeah.
Okay. Yeah. Thank you.
Yeah. Sorry about that. Okay. Any other questions about PMTs? Okay. So we'll come back.
I have a question here. Like just for, like, what's the efficiency? Like, if I had, I don't know, if I have 5 photons.
Yep.
How many electrons will I generate in the photocathode? Like, how efficient can it be?
Yeah. So the efficiency it depends on wavelength. And it also depends on the materials used. So say you wanted to get something in the UV, that would be very different from the IR. But what we talk about is generally the quantum efficiency. And with modern PMTs, you can get as high as, say, 60%.
Oh, I see that there's another question. Alex has a question. Go ahead.
I actually have 2 questions. The first one is, you said you're using oscillation cavity for the laser, and
yes.
That's because you want a broader range of wavelengths, let's say in contrast to by using a Gaussian cavity.
I just did a very basic overview of general lasers.
Okay.
The type of cavity choice that you have depends on what you want to send up in the atmosphere.
Yeah. And the second question is, at the first you're showing 3 lasers, and then it polarizes the beam.
Yes.
And you said something about angles. So is it you're trying to utilize the Brewster angle, or it doesn't have any connection, the Brewster angle, with all the measurements?
Sorry, I'm not understanding.
Okay, you said about the angles of the telescope.
Yeah, yes, this.
Yeah, so does it have any connection with the Brewster angle? Because
no, so this is just a geometric angle called the field of view.
Okay.
So depending on the curvature of your telescope, and also you can put a fiber in front of your detector to artificially restrict the field of view. There are benefits to having a large field of view if you want to do some very weak resonance measurements. But if you want to do, for example, daytime temperature measurements, you actually want a very narrow field of view to reduce as much sunlight as possible. So this is something you would choose when designing the system, is what the field of view of your telescope is.
Okay.
So I guess that equation is actually quite similar to the radar equation for a volume filling target.
Okay, yeah.
The z squared terms comes from the fact that it's sort of volume filling. The volume increases as you go higher up,
Yes.
up and up into.
Yes.
If it was just one single scatter, that would be actually z to the power 4.
Yes, but it's an angle correction.
Yeah.
Yeah. Ranging correction. Yeah.
Yeah.
Okay. Any other questions about so far? Okay. So after we have the light collected by the telescope, and put through the PMT, we simply count the number of pulses and sum them up over some time range, say a second, and we get a LIDAR profile like this. So this is a relative density profile, and what we see here on the bottom is log of photon counts. And this is what's described by the LIDAR equation. So a summary of this technical component: lasers are a lot of fun. We can have pulsed light that scatters off atoms or molecules. The ranging information comes from 2 times the speed of light times the time it takes for the photon to travel up and come back. Larger mirrors generally collect more photons. A PMT converts the single photons into a measurable signal, and the signal is described by the LIDAR equation. Okay. So here, if you'd like, I'd like to take a little bit of a 5-minute break, and I'm happy to answer any questions if you have, or if people prefer, we can continue on.
Maybe we can have a little break, but we can have some discussion during the break.
Yeah, that sounds good.
So I guess I have infinitely many comments here because I want to learn. I've already learned so much. Can you go back to that profile, that example profile that you showed?
This
that
one.
So that one, yeah. So I guess that bend here at about 20 kilometers, is that because of that focusing is that the Fraunhofer far field distance?
In this case, not. So in this case, I've artificially introduced something called a chopper. So I've cut the signal off at 10 to the 4 counts so that I don't saturate my detectors. So I have a spinning wheel in front of my detector, which only allows light with return time of flights greater than 20 kilometers. And
So you
this
don't want to
is just because it
saturate
takes
your
a
receiver.
little bit of time for this chopper to open up.
Okay.
Yeah.
So that's a protection of the photomultiplier, or?
Yeah, so each of these photomultipliers have a dynamic range. So in this case, I'm spanning 10 to the 4, 3, 2, 1, 0, 4 orders of magnitude. If you pay a lot of money, you can get more orders of magnitude. But if you put too much light on your detector, you start to lose signal. You saturate the detector, and it doesn't fully recover in time to count the next photon. And that effect is unfortunately quite nonlinear, and it affects you all the way up. So the smartest way is not to push your detectors to the limit. What we tend to do is we couple together a high channel, a medium channel, and a low channel. And say the high channel covers from 75 to 50, and then we kind of cut it off. And then the medium channel covers from 60 to 40, then we cut it off. And the low channel goes down, and we cut it off. And then we stitch them together afterwards to avoid really saturating our detectors.
So let's see these counts. It's I assume that's 10,000 counts is the peak.
Yes.
A little bit over 10,000 counts. And then you go all the way up down to 1 count, 1 photon.
Yes. Yep.
And that's per cent radar pulse?
This is probably an integrated plot. I don't know. It's several years old. I would guess this is about 5 minutes of data.
Okay. So in 5 minutes you get 1 photon. No, it must be, because the error bars are quite small. So maybe it is per pulse.
It could be. As I said, I'd have to look at the origin of this plot. I made this one quite a number of years ago.
Yeah. Good. Any other questions? How are you doing for time, by the way? We have 45 minutes left.
Yeah, so I have about 20 minutes more in slides.
Yeah.
And you
So we
said I have
plenty of
35
time.
minutes?
Excuse me?
How many minutes do I have left?
Well, 45 minutes.
Oh, okay, so we have quite a bit of time. I went quite a bit faster than I expected.
So that's good. Plenty of time for questions and discussion.
Questions, yeah. Any other questions now? Okay, well, I guess we can continue to the next section. It's more of a show and tell session. So it's sort of got a lot of pretty pictures in it. So here I wanted to give you an overview of what's possible to do with LIDAR. And I thought of many ways to organize it. And in the end, I decided to organize it by altitude. So we'll start at the boundary layer and then move up towards the thermosphere. I won't talk about CW LIDARs. I don't have a lot of experience with them, and they're mainly restricted to the boundary layer. And I won't focus much on the boundary layer at all. Again, I'm more of a upper troposphere to thermosphere person. But overall, I hope to leave you with a general sense of what you could do with a LIDAR without giving you too many details where it's overwhelming. And just to give you a sense of, if you're looking for a type of measurement, you could think of, is it possible to make this measurement with LIDAR? And if yes, can I contact someone who does this kind of work? Okay, so we'll start in the boundary layer. A lot of the boundary layer LIDARs are commercial. So they're generally small little boxes like this. You buy them from a company, you plug them into the wall and into an internet network port, and they just measure continuously. And they're really useful for things like airports, weather monitoring services, environmental agencies, pollution monitoring at certain sites. But they're mainly measuring wind speed, boundary layer height, cloud height, aerosols, water vapor, and trace gases and pollutants. Here's an example of what's called a celiometer. So LIDAR that's measuring the very lowest layers of the boundary layer. You can see that the measurement is very high resolution. This is probably operating on a kilohertz frequency, and it's probably eye safe, but it's really measuring these aerosol layers and these structures inside the boundary layer. It's really concerned with the air that we interact with daily and that we breathe, but it's really low altitude, so I know very little about it. To me, this is essentially geology. I just wait for these boundary layer LIDAR people to start talking about igneous and sedimentary rocks sometimes. So we'll move a little bit higher in the atmosphere to the free troposphere. This is a little more in my ballpark. So the main science topic in the free troposphere, so free troposphere in contrast to boundary layer, where the atmosphere is strongly affected by the surface, as opposed to the free atmosphere where the fluid dynamics are more important. The main science topics are very similar to the boundary layer: aerosols, clouds, water vapor, ozone, trace gases, temperature, and wind. These systems are also generally smaller. You often see them as mobile systems. So this is an example of a NOAA LIDAR for measuring, I believe, water vapor. So it's built in the back of a truck. They open the hatch for the telescope, for the laser to come out and the signal to come back. They just drive it to the location where they'd like to make the measurements, set it up, and let it run. That's one example of a very good tropospheric LIDAR implementation. Another popular way that tropospheric LIDARs are used is on satellites. So this is an example of a satellite that's been in operation for quite a number of years called Calliope, measuring clouds and aerosol in the troposphere. So you can see that as the satellite orbits around the Earth, it creates almost a curtain of measurements. So these would be the clouds that it's measuring from the top. So let's start with the first scientific topic, aerosols in the free troposphere. Why do we care about them? They're crucial for understanding Earth's radiative transfer balance and therefore climate change. If you look at the IPCC report, aerosols are a huge uncertainty, giving both positive and negative radiative forcing for climate change. And fortunately for us, though, LIDARs are the perfect tool for studying aerosols. We can do polarization studies that we touched on before. So we can determine whether the aerosols we see are pollution aerosols. In this example, this bottom layer is determined to be pollution coming from the Po Valley in Italy, or whether it's coming from dust sources. In this case, this dark red stuff in the top is actually dust that was evected from the Sahara. And these sorts of studies are very popular. They help both to see where pollution is advected to, and they also help validate weather models and advection within weather models. These kinds of studies are often done by comparing multiple different wavelengths of light. So instead of sending up just one laser beam, you send up 3 or 4 different laser beams, and you measure the same thing at different combinations of frequencies. And by conducting different ratios, you can tell different things from the same air volume. Most LIDARs in the world, I would say, are occupied in this sort of study, tropospheric aerosol studies, because it has such a vital importance for atmospheric science in general. This is a schematic of one of my favorite tropospheric LIDARs called Ralmo, operated by Meteor Swiss. It's in a container. It operates autonomously by itself. It has a telescope. The laser sends out the light. It's got windows on the top, and it measures water vapor, aerosols, temperature continuously all the time. It's a really nice, well-built system. The next topic I'll talk about are clouds. Clouds are also exactly like aerosols, really important for understanding Earth's radiative balance. And also, if you look in the IPCC report, not enough is known about them. They're really not well constrained currently. But again, LIDARs are really great tools for high resolution studies of clouds, just like they are for aerosols. So this is an example taken from a paper where they've used different colors of light and different properties of light to deduce different components of the atmosphere. So this top panel is just the normal backscatter. We can see that there's some sort of cloud layer happening here. There's some lower layer clouds here. And then the LIDAR is getting up much higher here because it's not attenuated. And then they took a look at the depolarization ratio. I won't talk about dye attenuation, but this is a different technique. And they took a look at the backscatter ratio. So they did this at different colors. So they took 2 or 3 different colors, and by ratioing the backscatter, they can tell something about the type of scatterer. So again, if you remember, the intensity of the scatter went to something about 1 over wavelength to the 4th power. So if I shoot a laser that's in the infrared and one in the UV, and then I ratio their backscatter, I can tell something about the size of my scattering target, because we know that the Rayleigh scatter is really proportional. It has to be proportional to the size of the scattering particle. So by combining all these different types of scattering information from a single LIDAR, they were able to deduce that this blue layer at the top that we saw was a liquid water cloud. These cyan parts were clear atmosphere, and these red and black were different kinds of aerosols and fall streaks, I believe. I have to look at the paper again. But by combining different sorts of information from a single LIDAR measurement, you can deduce composition and structure at the same time. Still on the topic of clouds, there's a lot we don't understand about how clouds operate, the microphysics of clouds. This is an example from one of my colleagues where she used a LIDAR at very high resolution, and she saw very thin layers, which she called laminations, within clouds. These structures are on the order of 7.5 meters to 150 meters thick. And they really permeate through the clouds. And she correlated the occurrence of these structures with snowfall. But alternatively, you could use these high resolution studies of cloud structure as a tracer for things like turbulence or small scale tropospheric gravity wave propagation. But the LIDAR really allows you to really get in there and look at the fine scale structure within a cloud. It's really very impressive, some of the stuff that people do on this.
Well, what kind of range resolution are you talking about here?
This particular LIDAR was operating at 7.5 meter vertical resolution and temporal resolution of 1 second. But again, you can choose what your resolution is by changing your delta T and delta Z in your counting electronics. So any other questions about clouds? Okay, the next topic that a lot of people focus on in the troposphere is water vapor. Water vapor is the most important greenhouse gas for climate change. CO2 is a very important gas, but water vapor has an extremely large absorption capacity for infrared radiation. The variability of water vapor, both in terms of time and spatially around the globe, make it extremely difficult to measure and accurately model. It's an extremely sensitive modeling variable as well. If you imagine a convective thunderstorm over an equatorial region, that's a really complicated physical problem to understand. You have to have inputting solar radiation, something about the surface, then transport of that energy into the water vapor, rising of the hot water vapor cloud, convection, overturning, rain. The entire system is a bit of a nightmare. And it makes water vapor studies by LIDAR a really hot topic. There are two techniques for measuring water vapor. The first is called differential absorption LIDAR, or DIAL, and the second is Raman water vapor using the Raman spectroscopy that we talked about earlier. So DIAL technique operates on more than just water vapor, so I'll give a few slides just to explain it. So the differential absorption bit means that you have to put two wavelengths out in the atmosphere. The first wavelength you put on a high intensity line of your target species, so water vapor. The second line you put on an off wavelength, so you put it somewhere over here. And then when you plot your signals, they're going to look something like this. So the off line will look really like atmospheric density, and your on line, so the red one, will have some structure that corresponds to absorption by this strong line. So if you do a ratio of these two signals and a bunch of math, you can work out an altitude profile for the number density of your target species. This is the fundamental of the DIAL technique, and it's applied to water vapor, ozone, methane, CO2, anything that you want to, any sort of trace gas where it can be otherwise very difficult to measure its number density.
So is this how you're basically separating the Rayleigh scatter from the
well, it's Rayleigh scatter at both wavelengths, but you're putting out one laser here and one laser here. These could be two lines, could be very close, or they could be separated by several hundred nanometers. The choice is really up to you. You just have to make sure that your scattering cross sections and your math are correct when you retrieve the target species number density.
So this is about opacity of the medium then, or?
Correct.
Okay, so it's Rayleigh scatter, the scattering mechanism, but then you're using opacity.
Yep, exactly. So more absorption in the red and less in the orange. So more opaque in red, less in orange. And then that's the differential absorption part. So here's an example of a free tropospheric water vapor measurement using water vapor dial. So you need, again, two wavelengths. The first wavelength is going to be strongly absorbed by water vapor. That's called P on. And the second will be weakly absorbed or not absorbed. That's P off. Then you ratio them, you put in some other correction factors, and you get plots that look like this. So number density in grams per kilogram, or as a percent mass ratio, a mixing ratio. And you can see that you can go from very low in the atmosphere to quite high using this sensitive technique. This is done by one of my colleagues in Canada. And this technique can often be automated as well. So a lot of automated LIDARs can do this quite easily. The second technique is called water vapor Raman. So again, if you remember back to our spectroscopy, there were some vibrational Raman lines off to the wings of our spectrum. And that's what we're going to be using here. So water vapor, because it's the molecule, can vibrate. So the H and O bonds can vibrate within the molecule. So what we want to do is we want to emit at one wavelength, say 532, and we want to measure this vibrational Raman at both the nitrogen wavelength, 608, and the water vapor wavelength, 660. We then use nitrogen Raman as a tracer for atmospheric density. So remember, N2 is 78% of atmospheric density, and we know water vapor is the variable component. So if we ratio water vapor at 660 over nitrogen at 608, we can get a mass mixing ratio for water vapor as a function of altitude. And this is what it would look like in a profile. And on top is what it would look like in a time series. So you can see water vapor also has these very fine layers and features. It can be quite variable in time and in altitude, which makes it extremely difficult to model and to properly account for in terms of radiative balance. So this is an older profile from 2012. So then any questions about water vapor? Okay, so the next topic will be ozone. Ozone is a really important gas to measure. In the troposphere, it's very bad for human health and agriculture. Ozone will destroy biologic tissue. So if it comes in contact with your lungs, it's very bad for respiration. It has a bunch of complex chemical pathways with automobile exhaust to form smog. If it's in sufficient quantities, it can hurt agriculture. So there's a real need to measure real-time atmospheric ozone near the surface, and also in the layers immediately above the surface, so say up to 4 to 10 kilometers. So I said it's very variable over short timescales and it's difficult to model. So the way we do this is also with the dial technique. So this is an example of an automated ozone dial LIDAR in the troposphere. This is a 32-hour measurement. And you can see the very fine scale structures, which can be very difficult to measure by sondes. So in this plot, we see these are radiosonde launches. And the sondes really don't give you a picture of how the ozone field is changing in time. They only give you these snapshots. But by having the LIDAR, it essentially gives you a sonde every minute or two vertically. So it's a very powerful technique. And many government and environmental agencies deploy these small automated ozone LIDARs all over the world because they're quite useful.
And it looks to me like you have better altitude resolution with the LIDAR than with an in situ measurement.
Yep. So sondes are in situ, so they move upwards at sometimes a variable speed. Sometimes you have better resolution, sometimes worse. Sometimes the sonde will blow 40 kilometers to the east of where you want to measure. There's a definite disadvantage to in situ measurements of trace gases. Also, in case people are interested, you can also do dial. You can combine dial with something called stimulated Raman emission from a deuterium cell. So in order to get your wavelength correct, you pass your laser light through a cell filled with deuterium gas, and then you emit the Raman shifted wavelength as your laser light. It's kind of a cool technique, and I learned about it when I was in France. It's really a very fun technique. Just sort of an interesting little side bit. Okay, so the next thing in the free troposphere that LIDAR people are interested in is trace gases. So these would be species, ozone we've touched on, CH4, methane is a big one. Methane is a huge carbon, greenhouse gas. It has quite a bit stronger forcing than CO2. And it's really difficult to measure, especially in places like the high Arctic. So this is a schematic of the satellite that was launched, or will be launched, I think, no, was launched, called Merlin. So it's a methane LIDAR. It uses the dial technique to measure surface methane emissions. Other examples of this are usually run by NASA. They have a high spectral resolution LIDAR. Jet Propulsion Lab, ESA has a few of these, but they're really for pollution monitoring and greenhouse gas studies. The big motivation for Merlin was Arctic studies for methane. As the Arctic warms, it will release methane from the permafrost. It's almost impossible to measure this without a satellite because it's so remote and so hard to get to. Okay, last thing in the troposphere is temperature. I'll go quickly. There are 4 ways to measure temperature. The first is Rayleigh-Briand scattering, which I'll talk about briefly, rotational Raman, vibrational Raman, and Rayleigh elastic Cabane scattering. Temperature is an important dynamic variable. It's also good for sounding and in assimilation into numerical weather models. It's just like a radiosonde. So typically, weather models assimilate radiosondes. The push now is to assimilate LIDAR temperatures. Okay, so again, just a reminder, Briand scattering is these little side lobes. If I were to measure that in the real atmosphere, it looks something like this. So these little side peaks look more like a 3-pointed hat. And depending on the temperature, these points are more pronounced, like this. So that's 555 Kelvin. This is 297 Kelvin, and it's a little more smoothed out. So by fitting this spectral shape using a line model, we can determine what the temperature is by the prominence of the Briand scattering peaks. Assuming that most of the atmosphere is composed of nitrogen. And the fit coefficient through this sort of structure gives you the temperature. That's the first technique. Second technique is vibrational Raman. So again, this is looking at these side lobes. What you're going to do here is assume that this side lobe is measuring only nitrogen, and that nitrogen is a good proxy for atmospheric density. Then you start at the top, you do hydrostatic integration all the way to the bottom, and you get a temperature profile. This can suffer some biases, especially if you have clouds or strong aerosol layers. You will get a distorted temperature profile. So what people generally do then is, instead of using the vibrational Raman for the temperature, they use the rotational lines. So if we remember back in here, I said that there is an asymmetry in the rotational Raman lines that depends on temperature. So if the temperature is high, then we have a high peak on this side and lower lines on this side. So by measuring the ratio of lines on the left and lines on the right of the Mi-Cabine's peak, we can determine what the temperature is of the gas. Oh, yeah, here's the bigger version. So the ratio of this red line over this red line, red is 300 Kelvin, and blue would be 220 Kelvin. So you can see as the temperature changes, the integrated area under these red and blue peaks change on either side of the Mi-Cabine's peak. And this will be independent of any clouds or aerosols. So it's a very robust, if somewhat more technical way of measuring temperature down all the way to the surface, where we can ignore things like water vapor, aerosols, ozone, pollution, all these other nasty things. It's a good and fun technique. Fourth technique is elastic Rayleigh temperature. So this is the temperature system. This is the type of temperature measurement that is typically done in the mesosphere, thermosphere, and upper troposphere. However, it can have problems in the presence of aerosols. So here I have plotted 3 different channels. So blue is a high Rayleigh elastic channel, purple is a medium elastic Rayleigh channel, and red is a low one. And what we see here is that at certain points, the temperature from the high channel gets bad, and the temperature from the low channel gets too cold. This would be an effect of an aerosol cooling, and this, would be an effect of this overlap correction on the high channel. But by combining a high channel, medium channel, low channel, and at the bottom, Raman channel, you can extend the temperature profile, now in green, all the way from the mesosphere down to the surface. So in this case, red and blue, so red is under the green in this one. Red is coming down like this, and it has a problem below 45. Blue is the next level of Rayleigh channel, so it's coming down like this, but then it has a problem below 42, a cold bias, and then below 30, it's completely wrong. And then you use the vibrational Raman in purple to extend it downwards. So by combining elastic Rayleigh and Raman, we can create one temperature profile for the entire atmosphere in green. So any questions for temperature? Okay, the last thing for the troposphere is wind. So many tropospheric LIDARs measure wind using ME scatter. So this, again, is the very strong central ME peak that's associated with aerosols or cloud droplets. This is an example of a wind LIDAR in China, and they measure winds based on the Doppler shift of light scattered off of aerosols. So if the emitted profile is this blue line here with the sharp ME peak, and the retrieved profile is this red one, we can see that there's this Doppler shift, this delta V DOP. And depending on how large this shift is, determines how large the wind amplitude is. And if the wind were blowing in the opposite direction, the red peak would be on this side of the blue peak. But again, this is light sent out, scattered off ME particles, so particles which are larger than the laser wavelength, and then the Doppler shift is measured and recalculated. Okay, and just a quick final summary of wind. We can also do wind with Doppler Rayleigh. So this was the Aeolus satellite, which operated for several years and was a complete game changer for numerical weather prediction. So this is Doppler Rayleigh. So they send laser light out along the line of sight. They scatter off atmospheric molecules, so N2O2, and also off of aerosols. And then the light comes back, they measure the Doppler shift, and they calculate here the line of sight wind from 0 to 25 kilometers over the entire globe. This was a real game-changing satellite from 2018 to 2023. I think you can see a real difference in numerical weather forecasting accuracy before and after the assimilation of this satellite data. It's a shame that they cut it off so soon, but it already has successor missions lined up and ready. Okay, so we're done with the troposphere. Let's move up to the stratosphere. What are the main scientific research topics in the stratosphere? Temperature, wind, ozone, water vapor, aerosols. So temperature. I wanted to give you a reference for how you can calculate a Rayleigh temperature. So this would be a temperature in this region, so below 50 kilometers down to 30. It's very similar to what I showed in the previous slide. You can go through this equation and math if you want, but basically we're looking at a gradient of pressure using the hydrostatic equation, and we end up with a retrieval for temperature, which depends on the mass of the air, gravity, and the pressure gradient ratio as a log. Okay. Why is this important? It's very important for gravity wave studies, polar vortex studies, which affect our weather, sudden stratospheric warmings, and global climate trends. This is an example of 4 long-term temperature LIDARs measuring temperature trends in the stratosphere. And you see they all measure something on the order of half a Kelvin per decade, cooling in the stratosphere. So global warming means warming only in the troposphere. Stratosphere, mesosphere will cool as warmer gases emit more light in the infrared. So next topic is stratospheric wind. This is an example of a wind LIDAR. Wind LIDARs always have tilted beams because you can't measure horizontal wind by looking vertically. You have to measure a line of sight with some horizontal tilt. So LIDAR is the only way to measure wind in the stratosphere, upper stratosphere and lower mesosphere, other than long-term radiosonde balloons, which can fly in campaign mode. The technique is based off Doppler scatter from molecules. Again, what we're studying are gravity waves, polar vortex, and dynamics. Really huge research topic, especially in the 90s and 2000s, was ozone. There was the huge ozone hole in Antarctica, and that motivated the construction of quite a lot of ozone LIDARs. So ozone studies are really monitoring the recovery of the ozone layer. I've shown 2 example profiles of ozone measured by LIDAR and by radiosonde. This technique uses dial technique to retrieve ozone concentration. And what are we really looking for? We're looking for long-term LIDAR data series. So a single instrument with a consistent calibration measuring ozone to determine what is the recovery of ozone as a function of altitude. And you can see that the recovery is both latitude dependent, station dependent, and altitude dependent. We see that there is not a strong recovery in the stratosphere, and in the troposphere, the results are extremely mixed and within the margin of error. The full ozone recovery report, you can read it in this book. It's fairly good, yeah. Ozone trends and uncertainties in the stratosphere. Okay, so we've done stratosphere. Now the last topic that I want to cover for stratosphere is water vapor. Again, 2 techniques for doing this, dial and vibrational Raman. Very similar to the troposphere. The stratosphere, unlike the troposphere, is very dry. However, we still want to measure that small amount of water vapor that's present because it's very important for radiative balance and also for chemistry and cloud formation and ozone destruction. So the small amount of water vapor that's present in the stratosphere can form what are called polar stratospheric clouds at high latitudes. And these clouds are responsible for the majority of ozone destruction. So measuring and knowing exactly what the water vapor distribution is in the stratosphere, even though it's very dry, can have large implications for the ozone recovery. Alternatively, just to say that the only other way of measuring water vapor at these altitudes with high resolution is to launch what's called a cryogenic frost point hygrometer, which is a very expensive radiosonde, and that's in the cyan here. And you can see that LIDAR, even though it doesn't have quite the resolution, is a good, cheaper alternative. Oh, sorry.
There's a question here. Julia has a question.
Yes, go ahead.
Yeah, I just wanted to ask if you're able to do actually predictions for the future with your data, or if it's like only for the now situation that you can see.
So that's a good question. Predictions from measurements are really tricky. I would avoid them. I even find predictions using models to have quite a bit of skepticism sometimes. Prediction is a very difficult game. I have a lot of respect for my modeling colleagues who do that. I'm nowhere near smart enough to try and make a prediction.
Okay, thank you.
Tendency also for experimentals to be very skeptical about modelers, and also vice versa. Modelers very skeptical about any observations. But are you referring, Julia, to the anthropogenic sort of cooling of the stratosphere, or what are you referring to with the long term?
I actually mean like in general, because you tell us the whole time what you can actually measure and see. You can measure the ozone, you can measure the winds, and so on. Many different stuff. And yeah, I think I kind of refer to the climate change, maybe a little bit.
So to answer your question here, these are 4 time series, and you can fit lines, and you can find out, okay, at this latitude, it's minus 0.39 plus minus 0.59 Kelvin per decade. I'm not confident in making a prediction based on that number.
Mm-hmm.
But say in the tropics, it's the uncertainty is much more. So this is a significant trend at 19 degrees latitude, where there's less variability in the atmosphere.
Okay, so you kind of can see trends, but it's like high data variability makes it hard to actually predict something. Okay.
Yes, exactly. The atmosphere is hard.
And I guess for the other prediction that was discussed is the sort of the short-term weather prediction, and I guess there the measurements really help because you have a better boundary condition that you can nudge your atmospheric model more more correctly. And
yeah,
so
currently
the more measurements you have, the more well off you are. And I guess there will be more and more LIDAR measurements because they will help with weather prediction.
There's a big push for assimilating LIDAR measurements in real time. Currently, a lot of the assimilation is done on radiosondes, which are launched at noon and midnight. So 2 points per day. Whereas if you have a LIDAR, you can continuously give a numerical weather model data every 5 minutes. That would be a huge advantage for them.
So on short term, you're actually able to predict a little bit, I get from this. I mean, now you have the aerosols here, and I think if you can see a pattern here, you would be able to see the next day the pattern to be moved. Am I right?
It really depends. I would not be comfortable in predicting more than a few hours in advance.
Okay.
Because if the weather pattern shifts, all of a sudden different air blows over your measurement. And this pattern that we see here can disappear in minutes.
Oh, that's
the air
fast.
mass shifts. Yeah.
Okay.
That's a good segue into these aerosol measurements. So aerosols, again, are super important for radiative balance, and they're a good tracer for mixing. So here we have very thin stratified layers, so we can tell immediately there's no strong vertical motion here. Otherwise, it would disrupt these aerosol layers. But they are static over the course of several days, 90 hours, these layers are persisting. So it's telling us something about how the atmosphere is circulating, that there's not a lot of shear, not a lot of vertical motion or mixing in the atmosphere in this particular time. And this is also becoming an emerging topic of interest for space debris. When you launch a rocket up into the space, 90% of the rocket is fuel. So all that fuel needs to be burned up in the lowest part of the atmosphere, and it produces things like methane, water vapor, NOx, a number of other compounds. That fuel then settles in these strong layers, and it just sits there. There's not a lot of mixing. It just kind of sits there and moves around the world for a couple cycles before finally being mixed out. We have absolutely no idea what that's going to do to the atmosphere. None whatsoever. Yeah. Okay.
Well,
so
maybe we know that it probably doesn't improve air quality.
Yeah, that's a good prediction. I'm safe with that prediction. Yeah, But you know, all this meteor, this space shuttle particles and things like that, that would affect cloud formation, both in the troposphere down here and also here in the stratosphere. And polar stratosphere clouds are huge ozone destroyers. And they are huge reflective, shiny clouds, reflecting light away and also infrared light back down to the Earth. So to correctly estimate the contribution of polar stratospheric clouds, that's a lifetime's work. Yep. Any other questions about aerosols, clouds, or the stratosphere?
Like this is a question, but this is all I know that you know about this topic, but like are there any ways that you could use LIDARs to study space debris, the influx of man-made objects into the atmosphere?
Yes, yeah. So there's a few ways you can do that. You can measure the upgoing exhaust from a rocket. So I reviewed a paper, I'd say about 2 years ago now, where a Chinese group claimed that they measured stratopause clouds. And I thought, oh God, there can't possibly be a cloud at the stratopause. And I worked out all the saturation vapor pressures, and yeah, absolutely no way there's a cloud existing there. And then I looked into it a little more, and they were upwind of a launch facility, a military launch facility in China. And then I looked into it a little more. What they actually measured was the exhaust plume of a military rocket. And it had formed, and it looked very much like a cloud, to the LIDAR at least. That would be one way to measure it. The second is as things come back down to Earth. So we're entering an era in the last 2 years where we're putting an exponentially large amount of tonnage of metal and materials into the atmosphere, into orbit, sorry. But also everything that goes into orbit eventually has to come back down. And when it comes back down, it burns up and vaporizes in the atmosphere. So that means that we're putting hundreds of tons of material per year into Earth's atmosphere with new and exotic elements like lithium, aluminum, silicon, copper, rubidium, all these other electronic elements that have never been in Earth's atmosphere before. We measure these all the time with LIDAR, but we have no idea whatsoever what they're going to do for ozone destruction, ozone chemistry, cloud formation. It's a huge unknown. It's really the Wild West.
Yeah, but with the LIDAR, you could measure their density in the atmosphere.
Oh yes, yes, yeah. That's what I'm having fun with now, is measuring lithium. Yeah, but we'll get to that in resonance in the mesosphere. That's next. So next section is the mesosphere. So between 50 and say 85 kilometers. So the main scientific topics, just like I said, were metal layers, often coming from meteoroid or space shuttle ablation, temperature, wind, and noctilucent clouds. So this is another nice picture of my fun little LIDAR in Kuhlensborn. So again, these green beams are measuring temperature and wind, and these purple ones are not measuring anything. I just put them up because they're nice, and there's 5 of them, and they're supposed to represent a small little mobile system that we built with 5 lines of sight with a UV laser. But since it's UV, you can't see it. So we made 5 blue lasers to represent that one, just for this picture. It was kind of fun. Anyway, it looked really cool. Okay, so metals. A lot of people in the mesosphere focus on the metal layers. So between 80 and I'd say 110 kilometers, you have a separation of the composition by mass, and you have a large amount of deposition of metals. So iron, calcium, nickel, aluminum, all these atoms, they form these layers in the upper atmosphere. Potassium, sodium, and they're really important for both mesospheric chemistry in these regions. So they all have complex chemical interactions with odd oxygen, hydroxyl, ozone, They interact with high energy photons. It's really a very complicated chemistry, which I don't fully understand. But normally, up before the beginning of the space age, all of these metals were in a rough sort of balance because their input function was meteoroids. And we know meteoroid composition to a degree, so that these metals were generally stable over long periods of time. They have their seasonal cycles that you see here, but otherwise they were fairly well known, and they were useful tools because we're able to use them to measure things like wind and temperature in this very narrow region of 20 kilometers. However, now we're getting new metals injected into this region. So as I mentioned before, I'm having fun with lithium. Also on my target, I want to try aluminum. The reason for those two is most of a spacecraft's aluminum plating is actually an aluminum alloy, aluminum lithium alloy, which is both more rigid and lighter. So as the spacecraft comes in, it heats up to about 933 Kelvin. And at that point, it quickly melts. So this was something that surprised me. I thought that it sort of broke off in little bits, but no, it really just gets up to this isothermal 933 Kelvin, and then it goes from a solid to little droplets. And the aluminum droplets continue on, but the lithium has a little bit higher melting or lighter melting point. So it immediately vaporizes out of these little aluminum droplets. So we get this trail of lithium vapor, and then the aluminum continues on a little bit, and then it too vaporizes. But yeah, most of a space shuttle shell just vaporizes in the above 60 kilometers, I would say. It's really kind of cool. Anyway, sorry, I'm getting distracted. Winds and temperatures. Okay, so how do we use resonance and Rayleigh to measure temperature in the upper atmosphere? We've already covered Rayleigh, so I won't talk about it again. It works just the same as the stratosphere. We talked a little bit about how to measure temperature using the sodium D2 lines. It's really from thermal broadening of the atomic lines. So we have this hyperfine pair of lines called the sodium D2 lines, A and B. At any given temperature, what you measure is a distribution like this. So for high temperatures, the lines are broad and they kind of overlap each other. For cold temperatures, the lines are much narrower and you see a pronounced minimum between the two of them. And then when you fit this shape, you're able to determine what the temperature is in this layer. So the top panel here is the sodium density measurement, and at the bottom is the temperature that's retrieved from this sodium density measurement, just by fitting the spectral broadening of the N2 line, or the Na2 line. Okay. And how do we measure wind and temperature with Rayleigh and a Doppler Rayleigh for winds and temperatures in the mesosphere? So this is what I do, a lot of what I do right now. So this is a measurement I made in Kuhlensborn. The top row is the temperature measurement from 35 to 90. So here's the time resolved temperature. The red is the stratopause, and the blue is the mesosphere up here, top of the mesosphere. And here's the nightly average profile in green, and the model ECMWF in black. It's really nice. And here's the zonal wind. So this is the east-west wind. Positive values are to the east. So again, we see the stratopause, or the stratosphere, and this very fast wind that we see down here is something called the polar vortex. So the large circular vortex of air that surrounds the polar regions during the winter months, and really controls the weather that we experience in Europe. So again, my measurement is red and the model is black. And then the blue at the bottom is the meridional wind. So north-south, again, we see the polar vortex, this reversal of the wind. So it's going from northward as positive values and then strongly southward and then back to northward. It really is a jet that happens just below the stratopause at 50 kilometers. So extreme wind shear is happening here. So from plus 110 to essentially 0 in just a few kilometers. So this is Rayleigh, Doppler Rayleigh to measure these winds. We can also use resonance to get a resonance wind. So before we used this sodium D2 line, the width of it to get the temperature. But if we measure these lines and they are shifted either to the left or to the right, that's a Doppler shift. And we can convert that shifted pattern into a wind speed. So again, here was the sodium measurement, and here was the retrieved wind speed, zonal wind speed. You can see it's slightly different than the temperature pattern. So here was the temperature, and there was the wind. Okay, that's that. The final topic for mesosphere is noctilucent clouds. I don't know if you see many really nice noctilucent cloud in Tromsø, you probably do. But they look beautiful just like this. And LIDARs are really excellent tools for measuring NLC because we scatter the me scatter, so the central component due to cloud particles, is so much larger than the Rayleigh. We can get really extreme resolution on these very thin clouds. So when you see an NLC, you know that they have to be at 82 kilometers roughly, but their width is so thin. They're dozens to hundreds of meters thick only. That's it. And what we're seeing, the zigzag pattern, is actually a gravity wave moving through the cloud. So that's really incredible. We can use these both as a tracer for the small scale dynamics of the mesosphere at 82 kilometers, but we also use these as a tracer for anthropogenic climate change. Noctilucent clouds are sort of a canary in the coal mine for climate change. Before the late 1800s, there were no NLC. NLC form in the summer months because the polar summer mesopause gets extremely cool. And as I think I mentioned a little earlier, climate change warms the troposphere, but it cools the stratosphere and mesosphere. So the more CO2 we put into the atmosphere, the colder the mesosphere gets. So the colder the mesosphere is, the more likely it is for a noctilucent cloud to form. So more carbon dioxide leads to colder mesosphere, leads to more NLC. So in that way, it's a very beautiful, but a little bit sad when you see a noctilucent cloud, because you know that ultimately humans are really responsible for that.
And I believe the methane is also converted
Yes.
to water.
Yeah. So that's the other tracer that is methane. So to get water vapor from the ground up to the mesopause, it's not very efficient. So Lyman alpha emission really breaks apart water vapor bonds. So what actually happens is methane that's released at the surface has to go up in the atmosphere and then get photodissociated into water vapor near 82 kilometers. So these clouds are water vapor clouds, but they were formed by surface methane. So it's another tracer for human influence on the climate, going all the way up to the edge of space. So there's no part of the planet that we don't mess up with climate change. But anyway, on to the next part of the atmosphere, the thermosphere. I promised you at the beginning that LIDAR goes up to 750 kilometers. And here's the last little bit that I want to show you to show what we can do above at very high altitudes in the thermosphere. So there's really not a lot of air above 100 kilometers. So not a lot of air means not a lot of scattering targets for LIDAR. There's a few things that we can measure. We can measure sodium atoms, iron atoms, and ionized versions of sodium, iron, and calcium. So here's an example of a sodium measurement happening from 100 kilometers to 150. So we see a large increase in the sodium atom number density occurring over the course of 2 hours. We can use these sodium measurements to work out temperatures and winds, but sometimes there's just not enough sodium for even that. But the cool thing about that is measuring the ionized versions of these metals, so the metal ions. And you can really see that there's a lot of really cool structure happening at very high altitude. Like, look at this band. That's really cool. And you know that the ions are really being influenced by the magnetic field lines and electric field lines much more than they are the neutral winds, because there's so little atmosphere up here. that the ion neutral collision rate is pretty low. So I would say that these ions are just sort of following the field lines. Yeah, that would be my thought. Okay, next bit. I promised you 750. This is something relatively new. Came out 3 years ago now. Okay, still thinking it's pretty new. Thermospheric measurements of metastable helium. People have been talking about this for decades, but it's finally been measured. So we talked a little bit earlier about how neon, krypton, and the other noble gases are pretty difficult to measure because their valence shells are full, and it's hard to kick a photon out of those full, complete shells. However, there's a trick with helium. Helium has what's called a metastable state. So it means that you're taking an excited helium, so it's excited already due to background conditions, and then you're stimulating that excited state up to an even more excited state. So it's a really, really rare. So most helium are down here in the ground state. Some are in this excited state, and we're stimulating this excited state population into an even higher energy state. And then there's a relaxation from this double excited energy state, so triplet state, down to the first excited state by fluorescence. And then we do the same thing we do with the sodium doublet line. We fit the observed spectrum. So there's two peaks here. Yeah, and we fit this observed spectrum. And depending on the fit, we know what the temperature is. So here is a profile from about 200 kilometers up to 750. It's a composite of 14 observations by season, I believe. So it's winter is the highest highest helium density. So this is summer, autumn, spring, winter. And you can see that the metastable helium population is highest in winter in the mornings and highest in winter in February too. But it's still an emerging bit of research, but it is, I think, the only kind of measurement possible at these altitudes with any kind of precision. Just to give you an idea, the integration bins look to be 50 kilometers maybe. So it's still very beginning stages for metastable helium research. Okay, so I won't go
just to point out, there's ionized helium could be measured with Arecibo at the.
Oh, cool! That would be really cool.
But Arecibo is no longer there.
Yes,
but there are some measurements.
Okay, so there are some.
Yeah.
Are there any other measurements up that high?
Not that I know of, no.
Yeah. Okay, so here's a summary table. I won't go through it, but it's a good, it's taken from a textbook. It just sort of summarizes all the things I've talked about. You can look through it if you'd like, but I'd just like to leave you some final thoughts. LIDAR is a really fun, active optical remote sensing technique. It's useful for high resolution studies of temperature, wind, density, and composition of trace elements. What you get out of it is 2D measurements in terms of time, altitude, and it's a useful tool to have in your scientist toolbox if you're doing atmospheric studies. It's not always the star of the show, but it's good to know what a LIDAR can show you. Okay, so with that, thank you very much, and if you have any questions, I'm happy to answer them.
Well, thank you very much, Robin. Any questions? Oh, Alex has a question.
Yeah, sure.
Yeah, about the NLC clouds in the last slide. It has a high value at 1630 UT time. Why
1630. Here.
Yeah, the high red value.
Yeah, so the cloud was very thick then.
Okay.
So this would be backscatter. So high red signal means many particles.
Okay. Thank you.
Yep.
Yeah, I wonder if you could see the cycling of temperature when you have these buoyant oscillations.
Yeah, that would be really cool. Unfortunately, our temperature retrieval gets messed up by the clouds. Because it's hydrostatic integration, when you go through the cloud, the measured density goes really high. So when you do dN by dz, it kind of blows up to infinity, right at the base of the cloud.
Any other questions, comments? I guess everyone is satisfied.
Oh, that's good.
Thank you very much. I guess we conclude here. I'm going to stop the recording and
Yeah, well, thank you very much for your attention, and I hope you enjoyed it.